convection plus radiation, and a few misconceptions associated with it in terms of MCQs and other things. Okay, all right. So convection would be transfer of thermal energy. Very careful about this. It's the transfer of thermal energy, not the transfer of media. So transfer of thermal energy in fluids due to a difference of densities. Right, and now is this setup. How does this work? Let's try to discuss that. Okay, so it primarily happens in fluids. What fluids would be? It's going to be liquid and it may be a gas, right? So this transfer of energy, or this mode of transfer of energy, will only be applicable for liquids and gases. Okay, so let's try to draw what actually happens in a convection or a convection current. For example, this is a beaker that we have, and we're trying to heat it up from just one corner. We can heat it up from the center, but we're trying to observe how the convection current actually takes place. So we understand from the previous lesson that if we heat up objects, if we heat up any substance, the molecular distance between its atom is going to increase. That eventually causes thermal expansion. The lowest thermal expansion you can observe will be in solids, slightly more will be in liquids, but infinitely more will be in gases. So liquids do expand, but not so much that it will be visible to you with your naked eyes. You can only experience its expansion by certain methods, but not over here. For example, a liquid and glass thermometer is an application of thermal expansion of a liquid, because mercury at room temperature is a liquid. So we have to create special circumstances in that thermometer, so eventually we can exploit that property of thermal expansion to eventually make a thermometer out of it. So over here we can assume to some extent that liquid is expanding, although it doesn't to such an extent which we are going to discuss right now. This will be exaggerated a little bit so that we eventually understand how this is actually taking place. So for example, if these are liquid molecules, of course they are not arranged in a regular pattern, we understand that from kinetic model of matter, but for the sake of discussion, let's say this is what it is. So when you heat it up, they become more agitated, and since they are free to move throughout the system, the distance between the particles, for example, if we exaggerate this scenario a little bit to understand what's happening, they expand outwards a little bit, right? And as a result, since they move to some new location, just so slightly, because they are expanding, right, their density decreases. Why do we say that the density is decreasing? Because density is content of mass in a respective volume. So if I had decided that this is the volume that I'm looking at, for example, that this is the piece or this is the space that I have decided for my matter, for the number of water molecules right now for the sake of discussion, then if some of the atoms, even if they were present inside, have left that space like this, and some of them are now out of that space, right? So it leaves less mass or less number of particles in that fixed amount of space for that given time, or for that respective instant in time. So eventually we will say, or we conclude that the density has decreased where the heating is taking place, because the particles are trying to move away from each other. So that respective volume that we were looking at doesn't have the amount of number of liquid atoms or liquid particles as it did when it was at a lower temperature. Do we understand up to this point? Yes or no? Alright, so when this happens, we can say that the density of the liquid that is closer to the heat source is less, but the density partially of liquid that is above that level, that hasn't gained any thermal energy yet, which is slightly colder than the water or than the liquid that is at the lower side, its density will be slightly higher for that respective instant in time because it hasn't heated up. It's not in contact with the thermal energy or the source of thermal energy directly. So what's going to happen? The liquid that has more density will appear to be heavier for that same system, and the liquid that has lower density will appear to be less massive or less heavy. As a result, the heavier part of the liquid will sink in this manner. So the heavier part of the liquid will start to sink because it's heavy, higher density, and the lighter part of the liquid that has heated up, which resulted in a lower density, will start to rise up because it is being replaced. It is being replaced by heavy water from colder parts of the liquid. Do we understand this point? Now, as a result, what's going to happen? The hotter part of the liquid is now at this location, and the heavier but colder part of the liquid is at this location. Now, this is in contact with the heat source directly. So what's going to happen? The process will repeat itself until the whole liquid has exchanged thermal energy and somehow has gained thermal equilibrium, that the whole system or the whole liquid is right now at the same temperature as it would be for the rest of the liquid. Do we understand this point? Yes? All right. So, okay. So now we write down the statement in a more scientific way, that how will we explain this convection or this convection current. This is convection current. Current means flow, right? So the flow of heavier parts of the liquid replacing the lighter parts of the liquid. This flow is known as the current, and the process has been given the name of convection current. So the liquid transfers thermal energy to different parts or regions of the system as a convection current is set up due to a difference of densities. Now, difference of densities, a convection current is set up, thermal energy is being exchanged to other parts of the liquid. These are key terms that must be a part of that definition. If you write them down, your definition will be accepted as accurate, and you will be given eventually full marks for this. Alright, so any problems in convection current? Now, convection, the similar idea or similar method or mechanism will also take place in air as well. So how do we prove that convection also takes place in air? There is a very simple experiment for this. For example, we have a candle in a box that is being lit like this, and it is placed inside a shoebox. Okay, so what we do is we light a matchstick, and then we just take it out. So the burnt matchstick releases some smoke over here, but the smoke doesn't go up. The smoke starts moving downwards through this air channel that is being set up. But why is it being set up? It's being set up because of this candle. Why? Because the air above the candle is being heated up due to the thermal energy provided by the candle. And as a result, that heat or that air that is around that candle leaves the situation, leaves this area, eventually being replaced by air from another side of the system, which eventually replaces the air for this one. And we see that the smoke stops rising, and it actually starts coming out from this side. So this somehow gives us the guarantee that air also experiences convection currents, or convection, or it also exchanges thermal energy in terms of convection. One more thing that you might have heard about is the sea breeze and the land breeze. Have you heard about that? That is also because of the convection current, right? You can go for the detail, or you can read the detail later on your own, because that's very simple. So we're not going to waste our time discussing that. All right. Okay, so we have some convection or convection current in air as well. Now let's try to identify our daily life examples where we may see these things happening at the same time, but we may not give them enough credit or give them enough observation to be able to actually be able to see them in that way. Okay, so convection in air and its related examples. So we have air conditioner, and of course, since the weather right now over here is quite humid these days, we do need the air conditioner, right? So how does that work? So this is where the air conditioner is installed, and we experience some cold air coming out of the air conditioner, right? And this is the rest of my room, of course. This is the rest of my room. So this is where we generally install the air conditioner, although it's not the optimum place where the air conditioner should be, but for the sake of understanding, let's take this to be that location. So it's providing cold air at this location. Now, just for the sake of understanding, cold air, should that be heavier or should that be lighter than hot air? Yes, cold air would be heavier as its particle would be less agitated, they would have less distance between the molecules, there will be more atoms per unit volume, and eventually it will be heavier. But hot air would be lighter as its particles will be agitated, will have more thermal energy, and as a result will have smaller density or less density. So cold air, since it's heavy, it moves naturally, it moves to the lower side of the room, settling down at the lower areas of the room because it's heavy. And eventually what it does is that it replaces hot air because hot air is lighter, so the hot air basically settles at the upper location of your room. You may have noticed this, that once you turn on the air conditioner, and let's say after 15 to 20 minutes, if somebody comes in your room, or even if you try to turn on the fan throws very warm air in comparison to the air coming from the air conditioner. Have you noticed that? That is primarily because of the reason, because the fan is installed in the ceiling right now, and the only air that it has access to is hot air. So because the hot air has settled in the upwards location, right? So it starts throwing that hot air downwards, forcing it downwards on you, which is quite unpleasant. So the ideal situation or the ideal scenario would be that you don't use air conditioner with the fans. That is the optimal way of using them. That is the most economical way of using them, because eventually what happens is that after a very long period of time, of course, not immediately, but after a very long time, what the air conditioner does is that it sets the room or divides the room in two parts. There is a region where the air is colder and there is a region where the air is warmer. And if you have installed your air conditioner to a very minimum height or to a smaller height, it keeps on circulating the cold air again and again. And once it starts doing that, it will project the air that is on the upper layer of the room, and it doesn't have to cool it down because you're standing at this location. So if the air that you are receiving right now is more comfortable or more pleasant, we don't need to cool down the rest of the room, right? So that is why it is advisable to install your air conditioner to a lower height, not to the very peak of the room, or not to the very highest point of the room. And this distinction, this is only created for understanding. It doesn't really exist. The whole room is basically divided into layers of temperature. So the lowest part may be at 20 degrees, the higher part may be at 21, this one be 22, 23 and 24. And of course, 24 is warmer, it is hotter in comparison to 20. Which is why when you turn on the fan, although it's also cold air, but it's warmer in comparison to which part of the room you are standing at that location, or you are standing at that point. Do you understand this idea? right? So this is also convection current. So we are using this principle using the air conditioners, right? Now let's try to see what's happening in the refrigerator or fridge where we usually keep our food to cool down. So two types of fridges, of course. One is something like this. We have a deep freezer on the top and we have a fridge at the bottom, and then we have a deep freezer that looks somewhat like this, right? So one compartment has a refrigerator, one compartment has a freezer. So we're going to discuss how it actually works. So what they do to make sure that the whole compartment or the whole area becomes cooled, they install the grill or the part of the area that is responsible for cooling it down at the most at the topmost area. Reason, if they had installed it at the lower part, it would only cool down the lower parts of the fridge. Why? Because cold air is heavier. It would automatically settle down and not be able to cool the parts of the fridge that are at the top. So what they do deliberately is install the cooling system or the cooling chambers at a higher location so that all the air in the chamber or all the air in the refrigerator would keep cooling down, falling downwards, being cooled. Hot air will automatically be replaced, right? So it would again start cooling it down and throwing it outwards. So this circle would continue unless the whole system has cooled down eventually, right? Do we understand this point? So every location or every system or machine that we've designed, we have kept these things in mind for the maximum benefit of the maximum or the optimum output at least, right? So this is our convection current. I would advise you to look at land breeze and sea breeze on your own. Okay. Then we have radiation. So radiation is purely the energy, basically the ultraviolet that actually causes us to heat up or causes us to feel heat or thermal energy from the sun is the ultraviolet spectrum from the sun. Although there are other spectrums coming from the sun as well. They are also responsible for some form of heating, but the primary one that actually heats us up to the greatest extent is the ultraviolet, right? Okay, so radiation comes from the sun or from any object that is at a high temperature. And primarily, this radiation is infrared radiation, not ultraviolet, but infrared radiation. And how is it heating you up? So, for example, if you were standing close to some logs that are set on fire, for example, on a bonfire or somewhere else. So you are standing on the sides, right? The hot air is rising upwards, but you are standing on the very side of that bonfire, or at least the source of the fire. But you would still feel some heat as you start walking close to it. Why would that be? Although the hot air is rising upwards, it's not traveling towards you, it's going up. You feel the heat because these sources, they are also emitting radiation that are actually directed towards you. So that is what happens if you put your hand close to or your hands close to a heating source. You don't see or you don't experience convection current, you are experiencing radiation. Even right now, if we're sitting in our homes right now, if we had the sun come out and it's with this complete brightness and radiation, the heat that we would be feeling is not because of convection or conduction. Conduction requires contact, convection requires medium, right? And radiation does not require any medium. So the energy that we're experiencing right now, we are seeing from the sun, is through vacuum. Okay, so radiation only the radiation has the capability that it can basically travel through vacuum. It doesn't need a medium to travel. It's still going to transfer energy from one point to another. Okay, and one small comparison between for radiation and the respective objects is with respective colors of the skin. So for example, if we have a bucket of water that is painted black and we have a bucket of water that is painted white, which one of the two colors or which one of the two buckets of water would you think would have water at a higher temperature after they have been left in the sun for some time? Which one of the two do you think would have the black one? Exactly, because it absorbs radiation much more or much greater or its absorption is much greater in comparison to the white surface. So this one basically reflects radiation away from it, which is why it doesn't experience the same change in temperature as the other objects. Do we understand up to this point? Right? So black surfaces or black painted objects are good absorbers and they are good emitters. So if they absorb energy very quickly, they also release thermal energy or radiation, of course, very quickly. Similarly, the process for the white surfaces, they are good, sorry, not good, but they are bad absorbers and they are bad emitters. You understand this point? Right? All right. When we have, this is the distinction that we do between the paint or the color, right? Then there's another difference that is for the texture of these objects. The texture, there are two types of them. The first one is dull, like a matte finish, and the second one is shiny, like a polished surface. So the dull surfaces are good absorbers and good emitters. Why? Because they don't reflect any, they just absorb everything because they're not good at reflecting. Shiny surfaces like metal or paint of good quality or the paint of the vehicles that we have, they are shiny surfaces, so what they eventually do is they end up reflecting most of the radiation that is being introduced to them. So they are bad absorbers and bad emitters. So we can combine these two things, the paint or the color with respect to the texture, and we can design a system that would be the best absorber or the worst absorber. Do you understand this point, right? So to put into plain perspective, best absorber would have to be black because it needs to absorb all the radiation, black, and it would need to have dull surface so that no reflection takes place and it takes in all the energy from the radiation. And the best, I would introduce a new word over here, the best insulator would be white and shiny. So you would notice that if you have a car, if you have a vehicle, if it has a shiny white silver paint in comparison to a car that has black, dark maroon, dark blue, or any darker shade of color, standing in the sun, they would both of them, although experiencing the same form of radiation, but the black car or the car that has darker paint would have a higher temperature of its own body in comparison to the white or shinier car, purely because of the reflection element, right? Okay, so a small point to be added over here, and that is that we see that in schools and colleges we have uniform for the students, and it is designed to have white in it. It's sometimes a white shirt, or for the girls it's white frock or a white shalwar, something like that. So why is that decided to be white universally? Because we knew this information, that white is a good reflector, right? So what we were thinking, or what we were expecting right now, was that if the students would go out in the sun, wearing white would help them keep their body temperatures low, right? So that is why, yeah. Exactly. Yeah. So that is why they're recommended to wear black, because black absorbs radiation. So they're just trying to help all the students or all the people who are actually try to regulate their body temperatures to absorb as much radiation from the environment as much as possible to keep it warm, right? So do we understand this point? Any issues? All right. So this is how we look at conduction, convection, and radiation. Okay. Let's try to solve a question that I generally ask my students. Now, for example, have you seen a baking oven that is driven by electricity, not the gas one, the electrical oven? Yes? Okay, okay, okay. So, for example, you have a grill at this location, for example, and you have placed some, let's say, some piece of meat or some vegetable, anything that you like to eat over here to cook it. And there is a heating grill on top of the electric oven, right? So, how does this eventually heat up the piece or the object that you want to cook? Is it using conduction? Is it using convection? Is it using radiation? So this is my electric grill, or you can say my heater, electric heater. How do we see this in the real life? So this is what you're actually looking at. So this is the window of that heater, right? The baking oven. And on some side of the oven, you may see the controls of temperature, time, and whatever you want to set for the oven, right? So the grill or the heater is generally installed at the top end of the heater. Sometimes it is installed on the lower side, but that actually reduces its efficiency. Then why is it installed at the top? And if it is, what method of thermal transfer energy or thermal energy is it using to transfer energy from the grill to the object that you want to heat up eventually? This is not a microwave, this is a baking oven. Mm-hmm. Mm-hmm. Hmm. Just a moment. Okay, so yes, your answer is right. We cannot say this is conduction because for conduction, it should be in contact with the piece of object that we want to cook, right? But there is one point where students sometimes identify that this is conduction or not, which it is conduction. Let me tell you where that is. Now, when it is radiating heat in terms of infrared radiation, it's also heating up the metal part of the sheet that on which you have placed that thing that you want to cook, right? So it is also absorbing thermal energy, and since it is in contact with the piece of object that you want to cook, so there is some form of conduction on the lower side of the thing that you're cooking right now. Do we understand this point? Yes. But this is not responsible for the majority part of the cooking, right? The majority part is responsible, or the responsibility is for the heating grill through radiation. So there is no convection. Even if there was some convection, the convection would cause hot air to rise up. It would eventually, or it would never reach the piece of object that we want to cook. So it's impossible. Like, it's not convection. But this is radiation. So radiation actually transmits energy in all directions. So what they do to eventually make this even better or increase its efficiency is that if this is the electric heater that they're using at the top of the baking oven, that is eventually hidden away from the sight of the user, what they do is install a reflecting grill at the back end of the thermal of this heater. So what happens is that as it is radiating energy to the front, if there is some energy being released to the back, that is also reflected. So you may see some ovens making a claim that this is better than the other one, this is more effective, this heats up food quicker, or this has some form of 3D heating or something like that, or it heats from all directions. So this is what they have actually designed in its own system. And the ovens who are less effective or less efficient or take longer time to cook, they basically don't install reflectors at the back of the radiation. And what type of reflector that is, or where do you see that? You may see this in tube lights. If you go to a hospital, you may see that the tube lights are actually hanging from the ceiling like this. And the shiny silver part that is at the back that helps reflect light downwards, this is known as a reflector. And it can also be used as a radiation reflector because that is also an electromagnetic wave, or you can say it also belongs to the spectrum of light, right? Do we understand this point? So a simple shiny surface or a shiny mirror can also be used to reflect radiation. So what they do is install a reflector at the back. This is just an extra piece of information to improve the concept of the idea how the radiation is helping cook food. Do we understand this point? Okay. All right. So we have done conduction, convection, radiation. Conduction was done in one of the previous lessons. Now we have done convection and radiation. This topic is complete. Tomorrow, I guess we will be starting with. Have you done momentum?